Hello, and welcome to a presentation by John Vitz, Matthew Pennington, and me, Chuck K. Mariung. I will start us off with some background on our project and insights from our exploratory data analysis. Our project is on hourly energy consumption forecasting based on data from PJM, which is available on Kaggle. PJM is an organization that operates the market and power grid for the eastern region of the US. Here's a map of it. And PJM Eastern is a subset that includes New Jersey, Delaware, Pennsylvania, Virginia, Maryland, and DC. We will mainly be using the PJM Eastern data subset, which has hourly megawatts energy consumption from 2002 to 2018. We also utilize an added feature of air temperature for one of our models taken from another source. Here we can see a small excerpt of the PJME dataset with hourly date time and megawatts columns. Our objective for this project was to develop several models that can forecast electricity use using this historical data. This kind of prediction has great value for power plants, which can plan ahead for better availability and for trading decisions in the energy market. We specifically trained models to forecast megawatt demand for 7 days, which is a typical period for trading scenarios. We also incorporated another dataset through the Meteostat API on historical air temperature for training one of our models. The data allowed us to add temperature by hour to the PJME dataset. We analyzed the effect of this added feature on prediction results, which we will detail at the end. Our approach is different from those of other contributors of the Kaggle dataset. We forecast out over a larger window of time, 7 days, and we use multiple models, including LSTM neural networks and XGBoost. We also incorporate air temperature data for training one of our models and conduct an analysis on how this affects performance. Now I will talk about some insights our data analysis produced. So we cleaned the PJME data and examined it with scatter plots, histograms, and box plots. We noticed that the spikes in energy usage were much more extreme than the dips, and that the histogram was right skewed. Graphs also show an obvious trend of cyclical spikes. Decomposing the daytime data into hours, weeks, and years showed the effect of each energy use. Box plots showed obvious trends by month, week, and hour of day. This matches temperature changes in season and habits of a typical household. Based on this, we predicted that month, weekday, and hour would have the strongest effect on models. We also plotted megawatts with the introduced air temperature data, which indicated as well a strong seasonality effect.
After our more visually intuitive data representations in the form of graphs, we decided to take correlation measurements. We decided to take correlation measurements in order to see if there were any obvious relationships we could draw between variables. One such relationship turned out to be the hour of the day, and it's strongly correlated to PGMU megawatts, so it's strongly correlated to power consumption. We then decided to measure the autocorrelation and partial autocorrelation of the megawatt data, and as it's in an hourly format, we don't have to actually format it in order to figure out how autocorrelated the different hour lags are with an original example time. And we have a pattern in the autocorrelation of the lags for 2 days, 24 hours times 2 days. This pattern suggests that the data for hours is serially correlated to some extent, which means that the current hour value for the amount of power consumption is somewhat related to and potentially dependent on, in a predictive model context, the previous hour values for power consumption. After taking the autocorrelation, we decided to do time series STL decomposition, and we decided to use STL decomposition because it's an additive form of decomposition that it can account for changes in seasonal patterns. We decided first to try to aggregate the data at an hourly level, and as you can see, it's a bit hard to interpret, although there does seem to be some patterns here and potentially some patterns here. So what we did is we resampled the data to the mean value for every month period, and by doing this, we can sort of smooth the data out and try to break down if there really is a trend component, a seasonal component in the data. And what we determined through this method is that while there isn't necessarily a discernible trend component in the data, there is definitely a discernible seasonal component in the data. After we performed the correlation tests and the STL decomp, we decided to go forward into the model building process by establishing a method for k-fold cross-validation for time series. This was done to prevent data leakage, as we don't want to be using future data to predict past results. We only want to use data in chronological order to predict for data that is after the trained data in chronological order. So we have this function that splits the data up, much like in this info graphic here. I also want to make a note that the difference between our split and this infographic is that our data starts with the trained data, so we've already taken the test data out, and our trained data is our trained data in our splits, but the test data is actually, in our case, validation data, because we've already separated the test set from the trained set. So this k-fold cross-validation is a separation of the existing trained data into trained data and validation data. The final part of this file involves using XGBoost regression for feature importance, and the reason I chose to do this was because it seemed like a decent way to try to experiment with including and excluding certain variables. So we utilized the cross-validation from before in order to run an XGBoost model that is otherwise constant via set seed and using the same input settings, and decided to compare the feature importance of different datetime objects and to measure them when we decide to include or exclude variables. So the first measure of feature importance, we decided to use all of the variables. Then we drop the bottom three in the second, and then we drop month in order to see what the effect would be on the others, because month is one of the highest actually, just to see what would happen. And something that was actually interesting that I found was that the fold each reflected a higher ability to generalize to the validation set for the set of XGBoost models that dropped the three unimportant variables according to feature importance, which suggests that we might want to do the same thing in an actual model in order to generalize better.
Hello, my name is Matt Pennington, and I'll be explaining the models we tested during our project. For each model, we split our data into a training and test set. The training data spans for the first 80% of our data from 2002 to 2015, while the test set is the remainder of our data from 2015 to 2018. We tested several models on our data, each with the goal of forecasting future megawatt consumption for the PJM Eastern region. Our baseline model is a simple statistical model using Facebook's open source tool, Profit. For establishing our baseline, we simply fed our training data into the model and produced a forecast for the remainder of the specified training duration, which you can see here. This model is very simple to implement and test, but had the lowest performance of any model we tested, with an R-squared of around 0.5937. Given the simplicity of the model, it can really only follow the vague trend of the actual data. As you can see, it seems the forecast in red is really just repeating year after year. It's not able to capture dynamic changes. So we tested another model, LSTM, which stands for long short-term memory. It's a type of neural network. This model is designed to output a 7-day forecast of megawatt load based solely on the last 14 days of historical data. We equipped this LSTM with 2 layers, one with 50 neurons and the next with 16. We found through cross-validation that this particular configuration slightly outperformed a single layer. We also found that adding 20% dropout in between layers was fairly useful in preventing overfitting. This model achieved a slightly better performance with an R-squared of 0.6593 on average. We also discovered that the LSTM forecast is more accurate for shorter duration forecasts, i.e. like 1 hour out, versus a 7-day forecast, where the performance sharply drops off. And that basically matches our expectations. Tested another model, also based on essentially the same architecture for the LSTM, except this one also included temperature data. This was motivated by the fact that there was a strong correlation between air temperature and electricity consumption, which you can see right here. Unfortunately, we found that adding historical temperature along with historical megawatt readings provided no real improvement in model performance. We hypothesized that there would be a benefit if we, instead of using historical temperatures, used historical forecasted temperatures, which would include information that is not already contained in the data set. And as you can see, the performance of this model was essentially the same, with the trend in mean squared error and R-squared increasing and dropping off as expected. Finally, we tested another model, XGBoost, which is a very popular model for Kaggle competitions. Unlike LSTMs, XGBoost is not often used for forecasting out over large windows of time. So we had to get fairly creative with how we modified the input and output data structures to match what we desired. Similar to the LSTM, we consume 14 days of historical data and output 7 days of forecasted data. To our surprise, the XGBoost algorithm produced the best R-squared of any of the models that we tested at about 0.69 on average. However, it took a very, very long time to run the model, somewhat over an hour. We also tested grid search on this model using a smaller subset of hyperparameters and found it took a very long time to converge on a solution. Looking ahead, there are several avenues to potentially enhance the accuracy and efficiency of the models that we've developed today. For example, in the future, we could include more external data sources, such as weather forecast data. Additionally, there seems to be room for further optimization. Given more time, we'd likely be able to substantially improve accuracy by training for longer and by utilizing grid search for hyperparameter optimization. Overall, this was a very challenging and rewarding project to pursue. We appreciate the opportunity to present. Thank you very much.